Hey Physics 2211. Today we're going to discuss Newton's second law and the momentum principle. The main question we're going to discuss today is if Newton's second law is consistent in theory and in practice, using a tracker model, filming a moving object to measure observable quantities like displacement and velocity, and a Glowscript computational model where we use mathematics to simulate motion with the same initial conditions as the tracker model. Here, we will compare the outcomes of both and see how accurately Newton's second law and the momentum principle can predict motion. First, we have to know what is Newton's second law. It's usually written as F equals mass times acceleration, or acceleration is equal to force over mass. However, acceleration and force are two quantities that are difficult to measure or directly observe, so we can use momentum to simplify this. Momentum is an object's tendency to resist change in motion. Momentum is equal to the mass times the velocity, and all moving objects have momentum. This is the same reason why you wouldn't want to step in front of a moving tractor trailer. With a large mass and a large velocity, it will resist change in motion, and that hurts. So how can we relate momentum and Newton's second law? By rewriting both equations, we can understand acceleration in terms of a change in momentum. This means that Newton's second law and the momentum principle are one and the same, and it gives us a relationship to describe an object's change in motion, which is the change in momentum is equal to the net force times the time the force was applied. In order to use the momentum principle in our tracker simulation, we had to make some assumptions. Our biggest assumption is that the net force on the rolling object is equal to zero. First, we observed a real object with an assumed constant velocity, and then we used the same initial conditions to simulate what should have happened based on the momentum principle. For the experimental procedure, a 12-gram cylinder was released from rest on an inclined plane about 10 degrees off the ground, and then its motion was recorded in the negative y direction once it hit the ground. This made it so that it had an initial non-zero velocity, but we began observing the cylinder while the net force was equal to zero, so the velocity was constant. Here you can see the rolling object in tracker, where I marked its position in the y direction every 1/3 of a second to obtain its final and average velocities. By analyzing the cylinder's motion and graphing its y position and velocity over 4.7 seconds, you can see that the magnitude of the displacement begins with almost a constant slope, but levels off at the bottom. This is more apparent in the velocity graph, where the speed of the object is constantly decreasing. Note that although the graph appears as if the speed is increasing, it is actually becoming more and closer and closer to zero, so the magnitude is decreasing. The Glowscript model was created using initial conditions from the observations, and then the resulting motion was compared. For example, the mass of the cylinder, the initial position, and the initial velocity were kept consistent. The incremental change in time was modified to equal the frame rate of the video, and the total duration of the model was extended to match the video. The net force was set equal to zero, and the y position and velocity of the object were updated and graphed. In the Glowscript model, you can see a very similar scenario where the object moves steadily in the negative y direction. While the motion of the ball is mostly accurate, there are some key differences in its analysis. For example, while the Glowscript model has a constant speed of negative 0.27 meters per second throughout, the video had a velocity beginning at negative 0.2 meters per second that decreased towards the end of the video. The position graphs of the two trials are similar, with the real-life example rounding off at the end, corresponding with a decreasing speed. This is apparent when comparing the two graphs of y velocity that they are similar, while the tracker graph decreased by 0.2 meters per second as the cylinder slowed down. We can explain some of these differences using two forces that oppose motion. Friction is the force that opposes motion when two solids are in contact. It's caused by the two surfaces sliding against each other as shown. Air resistance is the force that opposes motion as an object moves through the atmosphere, pushing air molecules out of the way. Both forces oppose motion, which could account for the decreases in velocity, meaning our experiment did not really have a net force of zero. You may be asking yourself, what if we conducted our experiment a little bit differently? If we had defined the motion of our cylinder in the positive direction instead of the negative y direction, would the result have been the same? The answer is yes. It's the magnitude of the cylinder's velocity that matters, not whether it rolls forwards or backwards. Here you can see plotted the positive change in direction versus the negative change in direction. The magnitude of the velocity is still decreasing. After understanding the differences between the model and reality, you might be wondering if it's possible to predict these differences or predict the component forces that sum to zero when the net force is equal to zero. As you saw earlier, it is possible to infer what forces are at play. Given more information, we could calculate the forces of friction and air resistance, as well as what force would have to be applied in the opposite direction to make F net equal to 0. This experiment is useful because it allows us to see how we can use the momentum principle to predict what forces are acting on an object or predict an object's motion given a net force.